This is a video I put together to help with one of my Chem Advantage AP Chemistry class assignments. The video is about oxidation reduction and a type of problem that you find quite often on the AP exam. In this case, we've got half cells and oxidation and reduction. This type of problem is pretty common. Here's an example I have of an AP multiple choice exam where you can see that they have half cells and they have the cell reactions in X's and Y's and 1, 2's and 3's and a whole bunch of questions. So this will be worth your time to learn how to do these things effectively and of course correctly. But before we do that, let's look at the materials that we have here because they're pretty interesting. We have three metals. In fact, with oxidation and reduction reactions, quite often you have metals that will either oxidize or, in case of their ions, reduce. We have some In, indium, we have V, vanadium, and Ti, titanium, with some applications that I think you'll enjoy listening about. But if not, you can always just fast forward to solve the problem. But spend a few seconds. I think you'll enjoy and be surprised at some of these applications. Here's their positions on the periodic table, titanium and vanadium, some pretty well-known transition metals. And here we've got indium right at the edge of things. Technically, it's a representative element, but down here, when you have this many electrons, you get a lot of metallic properties. Indium, and then, of course, its next of kin, which is tin right here, Sn. Let's start with indium, because that was the first item in our half cell one, indium. Here's the Wikipedia page on it. I didn't know that much about it before I was looking at this problem. Element number 49, they show it as a metal. When I was looking for other sources of it, surprisingly, I saw a number of cases where people posted images of them biting into sheets of indium because it's so soft to show that you could cut it with your teeth. I'm not sure that's the best use of indium. But when I did a little bit more research on indium, you can use it in its metallic form as indium in terms of a low melting conductor, but its compounds are amazing. A compound of yttrium, indium, and manganese. That's quite a set of tongue twisters, and it's called yin blue. It has an interesting characteristic of being one of the latest blue pigments made of inorganic compounds without any carbons. You can get plenty of blues with carbon compounds, but just using non-carbon compounds, it's been over 100 years since somebody has come up with an intense blue, and this one certainly is this beautiful blue. The other blues very often are toxic, so this one, which was cleared for production in 2020, is one of the interesting applications of indium. Of course, you're going to have some yttrium and manganese with it. The item that interested me the most was indium tin oxide, ITO. What surprised me is that its prevalence everywhere, because right now you're probably looking through a flat screen, and if it's a 15-inch flat screen, you're looking through about 0.5 grams of indium in the form of indium tin oxide. This compound is transparent if you get a thin film of it, and it conducts electricity. And with that property, you can set up things like touch screens and get all those electrons to move around with the liquid crystal displays. There's a site, Indium Tin Oxide, or indium.com, that says the metal that you look at the most is indium, and you're looking through it right now for this video. And because you can put a thin film of it on glass, as in the case of this Airbus cockpit window, you can run electricity through it, and it will produce heat that will melt any ice that forms on the windscreen. You might want to look up this ITO, or I guess you can say right now you're looking at it. So indium, a metal that I really hadn't heard of much, is one that you're looking through and what you use for all of our assignments on WebAssign. Vanadium is the other element in this problem. It's one that produces some oxides to protect it. It's used a lot in terms of alloys for hardening. It's named after the Scandinavian goddess of beauty, and one of the reasons for that name is they first used its oxides, and you've already heard in our oxidation reduction reactions that you've got vanadium, when it has different charges on it in solution, will produce these amazing colors. So they're beautiful colors, and hence vanadium. I'm going to skip ahead to titanium. It's very low density. It's extremely hard. It's a spectacular metal. And one of its uses is these little screws and plates are made of titanium. Titanium has this oxide layer that it forms, and with it, your body will not end up rejecting it. So it's safe to implant in bodies, and they're used to screw together bones that are broken to put in teeth. And here's some titanium screws that are put inside a foot to help these bones function a little bit better. But what interested me is that they are colored, but they're not dyed in terms of putting a pigment in them. Titanium, when it forms its oxide layer, is going to have its oxide layers come in various thicknesses, and the thicknesses will end up trapping light, and depending on how the thickness is, you can end up having certain wavelengths that are trapped or interfered with and produce almost any color that you want. Now, making an oxide layer in titanium isn't that difficult. In fact, here I'll show you someone that is doing it. The titanium is being oxidized and the hydrogen in the water is being reduced, hence the anode and the cathode.
Now I do have the voltage turned up high, so the longer I leave it in, the thicker the oxide will become.
The red is about 200 nanometers and the blue about 80 nanometers. That video was done by Multietch. They sell the solution that they use to make that coating with. What you would use that coating for toys, in this case pretty knives, dental industry in terms of implants, medical industry, all these uses of titanium, which are decorative and also quite useful in terms of industry and medicine. And here's an example of someone using just some simple borax solution in distilled water, a power source to generate a certain voltage. They're oxidizing this little plate on a bike that they wanted to get from its regular titanium color, that gray, and by putting some thin oxide layers on it and moving that solution around, they've got the electrode hooked up to the conductive solution, and then he's got the color that is desired. And you can see it's a really pretty gold that he put on his bike, just using a voltage source, some borax, and a titanium source. Of course, it's inexpensive, but going back to the dental applications where these screws are color-coded so that they're very easy to identify and use. In this case, you had ones that are like, say, 12 millimeters in length, which are one color, and 14 millimeters, which are another color. Even though they're relatively inexpensive and easy to produce with titanium, a single screw might cost maybe $30 at the very most by the time you finish processing it. By the time it gets used for medical applications and gets into your foot, this would be the bill that you'd pay for those 4 screws. 2 screws, which are 12 millimeters, $7,500, and another 2 that are 14 millimeters, $15,000 for 4 of those tiny screws that you saw embedded in that foot. Impressive. Well, let's go from our titanium, vanadium, and indium to the problem at hand. Here it is. And this is an impressive problem. When I looked at this, I said, oh my gosh, I've got half cells and indiums and solids and aqueuses and X's and Y's and Z's. How can I end up handling this? These types of tables and problems are found in FRQs and multiple choice questions. So how can we answer these questions relatively easily? That's what we're about right now. So let's get our logical thought going and see what we can do for this. Based on the reactions of cell X, cell Y, what is the correct ranking of the standard reduction potentials of the indium 3, vanadium 2, and titanium 2 ions? Reduction potentials. How well do they end up reducing? This is pretty complicated and you're not sure where to start. Well, start with the half cells. And I recommend that what you should do is just draw them. We've done this before. We've drawn these half cells. And with this visual, you can get the idea of the metal here, the indium, soft metal that you can bite through, and the indium ions that you can make a tin oxide with and look through to solve this problem. So this makes things a little bit simpler for me. I mean, you can look at this equation, or you can say, okay, here I've got this half cell. Now it's got a voltage of 1.29 volts. That makes it a little bit simpler for me. And it is both half cell 1, which is the indium, and half cell 3, which is the titanium. So there is our other half cell. One of the nice things about oxidation reduction, you don't have to worry about two items, the oxidation and the reduction. So here's the other half of the cell. Now, if I was doing this problem, I probably wouldn't draw on the salt bridge. I'd just make a quick sketch to clarify things for me. And this does. I know I see galvanic cell X, and I see it's got a half cell here and a half cell here, and they give me its voltage 1.29. This is a lot clearer to me, and it's worth the time. Typically, these things will be 4 points, like 4% of the entire AP exam. A little drawing is going to help. I wouldn't have done the salt bridge if I was taking the test, but I'm your chemistry teacher, and it would be negligent of me not to put this salt bridge in that would allow the ions to balance. Well, reduction potentials. I'm looking at the reaction, and I see the indium plus 3 changing into indium solid. It's going from a plus 3 to indium solid. The oxidation number is going from 3 to 0, so that's reduction. It is gaining electrons. You gain minuses to reduce. You get that negative charge. Origin of the word is that when you took oxides of metals and finally got the metal, you had a smaller pile of metal. So we know the indium is reducing, gaining electrons, so I just draw my arrow there. And I know that because here they've got this equation, and it's got a voltage of 1.29. So we know immediately that indium is better at reducing, that is, getting electrons, than titanium. It's ripping the electrons off this titanium, which is going to titanium plus 2, and probably this titanium is changing colors as it does so. We already know the ranking that indium is better at reducing, going from plus 3 to 0, because it's oxidizing the titanium. The titanium is being oxidized. Indium ions turning into the metal. We'd see some soft metal crystals growing here. Here's a short video from the kidssshouldseethis.com showing the formation of tin atoms from tin ions in solution at a cathode. The tin ions in solution are picking up electrons and depositing on the cathode. But this titanium is going to be oxidizing like mad because indium is better at grabbing electrons than titanium is. Hence our oxidation reduction. Okay, I've got one thing drawn. I've got X. Here's my X, and I've answered half the problem. This diagram will come in handy later too. So let's look at galvanic cell Y. And I've got my indium. Now it's attached to and reacting with vanadium. So my other cells can be vanadium. And I look here again and say, oh, indium's ripping electrons off of vanadium, and it's got a voltage of 0.84. I've got my diagram, and I see my indium, arrow time, crystals growing, and my vanadium oxidizing away, producing a vanadium plus 2 solution, and I'll reveal my electron flow. In order for this plus 3 to become IN0, it's got to have electrons. So the electrons. Now the reaction is occurring actually because a voltmeter has high resistance, but it has potential to go. If I connected a wire, the current would flow and we'd be growing our crystals. And our salt bridge would have ions that would balance the changes that we have in these solutions. So now I know that vanadium is not as good at reducing as indium is. But look, here my voltage is 0.84. Indeed, the indium is ripping the electrons off vanadium, but vanadium is holding on to them better than the titanium is. Indium here is getting a voltage of 1.29. It's having no problems ripping the electrons off the titanium compared to the vanadium. This flow is huge. So answering my question based on the reactions of cell X and Y, and I drew them so I could figure out what's happening. This is so much clearer to me than all these letters and aqueuses and the rest. So I can confidently say titanium was my weakest character. Look, it lost its electrons like mad. Then vanadium was next, and we can probably subtract that difference and find an interesting voltage difference between these, and we'll pick that up for later parts of this problem. Now, finally, our champion at reducing, the substance that's going to rip electrons off the best, is indium plus 3. In fact, you'd say, I'm worried about this indium plus 3 because it's so good at reducing to get its electrons to turn into indium. If I put my hand on it, it will rip my electrons off. Well, that takes care of A for this problem. Now we're going to attack B. Well, not really now, because you're going to have to go to the next video to see how to solve this problem for the net reaction for C and also the standard potential for the 2 half cells. So pick up the next video and you'll get the next exciting chapter of this amazing AP chemistry question.